Hey guys, hope you're having a fabulous day. I want to wrap up this unit on law of sines, law of cosines, along with all of our polar stuff, I guess you could say, with polar graphs. This is going to be kind of a culmination of everything we've talked about with the polar coordinates, the polar equations, and now we have the polar graphs. So if you haven't done your polar coordinates yet, you're definitely going to want to, because we're going to jump straight in to our first example, and we're going to need to be able to plot some points. Now, just like everything with Algebra 1, maybe Algebra 2, whenever you introduce something new that you want to graph, you want to make an XY table. Well, since we're talking about a polar graph, instead I'm going to be making an R theta table. And I like to plug in theta. That is it's kind of my dependent variable, I guess. I'm sorry, independent variable. And so if I can plug in different values of theta, that can in turn tell me what R is. So I can really plug in any value of theta that I want to. I'm just going to plug in all the values that are on this graph. That's a really good start for most of the ones that we're going to be doing. So I'm just going to be jumping every pi over 6 units, or 30 degrees, and writing these down. And I get pi right there. And so what I'm going to do is I'm going to plug in all these values in for theta. So for instance, I'm going to plug in 0 in for theta. Well, cosine of 0 is going to be 1. 4 times 1 gives me 4. So it just turns into a plug-in chunk. If I plug in, say, pi over 6, so that gives me 4 times the square root of 3 over 2. That gives me 2 square roots of 3, but that doesn't really help me in graphing it. So I'm going to hit 2 times the square root of 3 in my calculator. It gave me like 3.5. Do the same for pi over 3. Kind of see where this is going. I plug in pi over 3. That gives me just 1/2. Okay, so it's 2. And some of these you can just do in your head. Cosine of pi over 2 is 0. 0 times 4, well, 0 times anything gives me 0, including 4. 2 pi over 3, well, if I plug in 2 pi over 3, I get negative 1/2. I get negative 2. 5 pi over 6, I get negative square root of 3 over 2. That just be negative 3.5. And if I plug in pi, see, cosine of pi is negative 1. Yeah, it gives me negative 4. Okay? So there's half the points that I want. Okay, let's go ahead and plot these, though, and see where they land. So radius of 4, my angle is 0. 1, 2, 3, 4. So that's going to land right here. If I go up pi over 6, I'm only wanting to come out 3.5. If I go up to pi over 3, I only come out 2. 1, 2. If I go to pi over 2, I don't go anywhere. So I'm just going to sit right there on the pole. Anytime your r is equal to 0, it doesn't matter what your theta is, you're going to be sitting on the pole. Okay. Now here's 2 pi over 3, but I've got a negative in front of it. So it's actually going to go in the negative direction towards, say, 5 pi over 3. 1, 2 units. Same thing. And up the last point landed right where I already had a point. So what I want you to do is I want you to do the other half of the r theta table, because we haven't done 7 pi over 6 all the way to 2 pi. So there's going to be a lot of times in this video that I'm going to ask you to pause. I'm not going to do 2 pi because I should get the same thing I had over here because they're coterminal. So I'm going to ask you to pause the video. I want you to fill in those r's and go ahead and come over here to the table or to the graph and plot them. When you fill in that table, you do get the same values that you had over in the blue table. And when you come over here to the graph, you get all of your red dots to land on top of where we put the black dots that came from the first table that we did. So we have some redundancy there. That's good news. That means that I'm going to be able to cut down all of our work by half on all these problems. Okay. So if I connect these, with a smooth curve, I just get a nice circle. And that's the first polar graph I want to talk about, is just a circle. Oh, before we do that, I do want to talk about test for symmetry. Okay, let me actually come back to that test for symmetry. I want to go ahead and talk about the circle. So anytime I have a circle, it's always going to be tangent to the pole. All right, it's always going to have one point right there on the pole. I guess what we did part A over here. And so whether or not A is positive or negative tells you whether it's going to be on the right side or the left side of the graph. Or if we're dealing with sine, it tells you whether it's above the graph or below the graph. Now, just looking at this, I see that I have some symmetry. Okay? For cosine, my graph is always going to be symmetric with respect to the polar axis. And anytime I have sine, like I have here, my graph is always going to be symmetric about the line y equals pi over 2. Or, yeah, y equals pi over 2. Okay? And that's what's stated on this slide that I skipped. So we're not going to be looking at secant, tangent, cotangent, any of those. Everything's going to be in terms of either sine or cosine. And so like for the example that we just did, it was cosine. Whenever I graph something that is going to be a function of cosine, and cosine is in my equation, then I can just simply make it so it's symmetric to the polar axis. So whatever is above the polar axis will also be below the polar axis. I'll illustrate that in a minute. Well, if my graph has something to do with sine, it's going to be symmetric with the line pi over 2. So I might have graphed a circle that looked like this. So I come down and touch the pole. That means that the left side has to be the same as the right side. So it has this vertical line of symmetry. So let's try it with our next shape. It's not going to be a circle. It's not going to be a circle because this 2 is coming into play right here in front. If I just had 2 cosine theta, then yeah, it would just be a circle again. So let's take a look at this. I'm going to make my r theta table. You guys are going to have to watch me in this video on the r theta table. I have a really bad habit of putting my thetas on the left underneath my r and my r's underneath my thetas. So hopefully if I say that out loud, I'm going to catch myself and not make that mistake again. So I have another function of cosine, right? What that whole idea of symmetry is that I just need to put in the top half of my graph. Or I could do the bottom half. I usually choose the top half of my graph, and those are going to be the angles that I use. Going down my theta table. I don't have to worry about this bottom half because it's going to be symmetric. Everything we graph is going to be symmetric. And so we'll pick up on that later on. So I'm going to plug in 0, pi over 6, pi over 3, pi over 2, 2 pi over 3, all of these angles in for theta this time. Okay? Still plugging in for theta. And so whenever I plug in 0, I still get 1. Then I get 2 times, 2 plus 2 times 1. Well, that's just going to be 4. If I plug in pi over 6, that's going to give me that nasty decimal. So I'm just going to hit 2 plus 2 cosine of pi over 6 in my calculator. And it gave me 3.7. Okay, pi over 3. I could probably do that one all right. Cosine of pi over 3 is 1/2. Half of 2 is 1. 2 plus 1 is 3. That one wasn't too bad. Cosine pi over 2 is 0. So that should just take it down to 2. 2 pi over 3. Well, that's just going to make it so this is negative 1/2. So it'd be 2 plus a negative 1. Let's do 1. 5 pi over 6. I'm going to go back to my calculator on that one. 2 plus 2 cosine 5 pi divided by 6. That was like 0.3. And then pi is probably not going to be too bad. Yeah, it's just going to be 0. Cosine of pi is negative 1. So I get 2 plus 2 times negative 1. So 2 minus 2 gave me 0. So that's as long as my table needs to be. I don't need the whole second table for the bottom half this time because I'm just going to reflect all my points. So I'm going to come over here, put my points again. Just picking the points off the table. 1, 2, 3, 2 pi over 2, 1, 2 pi over 3. No negatives this time. I lucked out. We won't be that lucky throughout this whole video. But that's half my points right there. Okay? My other half of the points are going to come by just reflecting these blue dots straight down. So if I reflect 2 pi over 3, it's going to land right here. If I reflect this pi over 2 point, it's right here. I just keep going. I'm just reflecting straight down all of these points. So my final shape on this, whenever I go to graph it, it forms a heart. And that is my next shape, is a heart. We unfortunately don't get to call it a heart. We're going to call it a cardioid. A cardioid. And so a cardioid, again, it can be facing any which direction, but you're always going to see the vertex part of the heart where it comes in, or the cardioid, to be right there at the origin. And the reason that is, the reason that I know that I'm going to have a cardioid is because if I look at A and B right here, A and B are always going to be the same on all of these. Now, whether I'm dealing with sine or cosine and whether or not I have a plus or minus in between is going to show me which way my heart is facing. I don't have to memorize it, I don't even have to write it down, but my table will spit all that out for me. But just know that it can face any direction, okay? And it will probably on some practice problems that I give you later. Go to our third shape. We have a lot of shapes, guys, and so I'm just wanting to touch them all. I'm going to be maybe going a little bit fast, but you can go back and definitely watch the video. R theta table. On my R theta table, now this time, look, what's different about it? I'm dealing with sine. If I'm dealing with sine, that means that I'm going to be symmetric with respect to this line, this vertical line. And so I just need to plug in all the points either on the right side of this line or all the points on the left side of this line. It doesn't matter which one, whichever points you think look nicer. I'm just going to randomly choose one. I'm just going to do the left side. So my table, I'm going to start at pi over 2. And I am going to work my way down all the way down the left side of this graph. 4 pi over 3 and 3 pi over 2. Okay, I'm going to give you a little bit of play in this one. I want you to go ahead and plug those values in. Now we're dealing with sine this time, but plug in these values right there for theta and get your R values. And go ahead and come over here and plot them, and then we'll reflect them and draw our final product together. Here's where I got my points to land so far. Okay, now I can reflect over all of my points, and so this is going to land at 1.4 right here. This one's going to land at 2.5. It's kind of some tedious work here. 1, 2, 3, 4. This one lands at 5.5. Like way out here. We had to extrapolate a little bit. It's okay. And so if I connect these with a smooth curve all together, it kind of looks like a cardioid, doesn't it? And it's still in the cardioid family, but the idea is that if it does not come down and touch this pole right here, it can't be a cardioid. All right? So we need a new name for it, and the name is a limison with a dimple. So the dimple is going to be kind of this pushed in area. We graphed D over here. It's going to be this pushed in area right here. And so looks a lot like a cardioid, but it's not. And the reason I can tell just from the beginning that it's not going to be a cardioid, if I go back and look, is that my A is going to be larger than my B. Okay? In this case, 4 is larger than 3. So anytime I'm going to have a limicone with a dimple, I'm going to be looking at all of these A's being larger than B. Whether it's plus or minus, it doesn't matter. Cosine or sine, that's just going to change the orientation of it. I'm going to get a limicone with a dimple. It's just fun to say. It reminds me of that football player, Pierre de Garçon or something. And so I like it. Well, you can kind of think of what's coming next. What if A's not bigger than B? I'm glad you asked. What if B is bigger than A, like we have here? Well, let's see what it's going to look like. R theta table, all of them, what they're all going to get. Now, we're dealing with cosine this time. So when I'm dealing with cosine, remember my line of symmetry is going to run right through the middle of my graph horizontally. So you can do the top half, all those numbers. You can do the bottom half. I always choose the top because those numbers are nicer. Okay. So go ahead and make your table, plot your points, and you're probably going to need some help reflecting them. So we'll just go ahead and make the table and plot the points and stop there. Okay, so go ahead and hit pause and let you guys work that. This was looking pretty weird. Now, I had a big jump from here to here on this. So I am actually going to, I'm going to need to do this some. I'm going to need to go get another angle. So I'm going to pick up this 7 pi over 12 angle that I skipped between pi over 2 and 2 pi over 3. So 7 pi over 12, I'm going to wedge it in right there. And I'm going to figure out what that is. It's obviously going to be a decimal. 2 plus 5 cosine 7 pi over 12, 0.7. I want you to see that 0.7 point right here because I really didn't just jump straight down. It still is going to be a smooth curve coming down. Okay? And it might help to go ahead and graph what we have so far. Now, it looks like just a random scattering of points, but keep in mind the order in which we made this table. That's going to help. It came around, I hit this green dot, I hit here. Kind of got a spiraling action going on that. Okay? Now, remember it's symmetry running horizontally through the middle of this graph. So all of these dots I can also reflect up. I can take this dot that's down here at 5 pi over 3 and reflect it up to pi over 3. I'm seeing where exactly it landed at as 1/2. And this green guy, he can come down and he's actually going to be right here. And then this pi over 2 that was here, I'm going to reflect it down to here. I'm just reflecting all of my points. Where was I? Right here. And then I extrapolate it a little bit. There we go. And so if I continue my smooth curve through my dots, it's going still in the same order of my angles. Kind of looks like a cardioid, doesn't it? But it's got this little thing going on in the middle right there. And we have a very, very scientific and mathematical name for this thing right here in the middle. It's called an inner loop. So we call this one I call it a limicone with an inner loop. And so, again, it can be facing any direction that we want it to, depending on whether or not we have a plus or minus in between our A and B, and whether we're dealing with sine or cosine. Again, the table will spit it out for you. And so, but notice in all these cases that A is going to be less than B, and it should give me a shape that looks like this. Now, this is normally where we call it a day. I'm going to go ahead and just go straight into this next video. I'm going to try it at least. If not, I have a backup plan. But we will, let's just do some more of these shapes and see what we can get. Okay. So this one's a little bit different. It's got an r squared in it right here. And we're dealing with cosine. So if we're dealing with cosine, remember that's still just going to be the top half of my graph. If we don't get some more sines in here, we'll come up with some. So if I make my r theta table, make sure I'm putting my angles on the right side. I've already had to redo this video once. And again, I'm just going to go from 0 You're going to know the order of this table, that's for sure. All right. And I do a little bit of work on this, and it's actually going to help me out a lot. Now, this isn't going to be an r squared right here. It's just going to be an r. Okay, so keep that in mind when we work this. So I'm going to plug in 0 in for this theta right here. And if I plug a 0 in for this theta, that gives me 2 times 0 is 0. I'm taking cosine is 0. It's still 1. I get r squared is equal to 4. So my r would equal plus or minus 2. Great news. I got 2 points for the price of 1. I got the point 2, 0 right here. And I got the point negative 2, 0 right there. Just went in the negative r direction. Awesome. Well, let's keep going. That was good. Hopefully I can get 2 points on all of these, and I won't have to go nearly as far down the table as I thought I would. So let's plug in pi over 6. Well, 2 times pi over 6, that's going to jump me up to pi over 3. Let me write out what I'm doing. Feels like I'm going maybe a little fast. Cosine pi over 3, well, that was 1/2, right? I'm starting to doubt myself. I've done enough of these. So I get 2. Yeah, r squared is equal to 2. So my r is just going to equal plus or minus the square root of 2. And the square root of 2 is like 1.4. So I get plus or minus 1.4. I've already got 4 points. I think I'm going to have a pretty good idea of what this is going to look like. So now I didn't plug in pi over 3. I plugged in pi over 6. So 1.4 would be like here. And negative 1.4, I'm going to go this way. Back right here. You guys remember the symmetry on this one? So if I go ahead and reflect, this point up has to land right there. And if I reflect this point down, it's going to have to land right here. So that was helpful. So I might have enough points already. I could try pi over 3, but if I just kind of go in order of my angles. So I went from here. Let's get one more. I know I've got that much. I just want to be safe on this. Pi over 3. If I double it, that's going to be a 2 pi over 3. Okay, so I have 4 cosine of 2 pi over 3. See, cosine of 2 pi over 3, that is going to be negative 1/2 times this 4 is 2. So I end up getting the same thing. My r is going to equal plus or minus the square root of 2, 1.4. So at pi over 3, I'm also at plus or minus 1.4. And then down to right here. Let me backtrack my steps on that. All right, so trying to do too much in my head. Yeah, that does give me negative 1/2. That's going to be r squared equals negative 2. That point's just not going to work for me. Okay, and I'm going to start getting a lot of repetition on this. I actually do have enough to go ahead and graph this, okay? And so what this is going to look like is, kind of looks like an infinity, right? That's not really what the shape of it's called. We're going to call it a lemniscate. A lemniscate. Not many points to plug in on a lemniscate. But the big thing that's going to give away that it's a lemniscate is the fact that you're going to have an r squared on that left side of the equation. That's going to be the only one that we have an r squared on. Okay, and so the lemniscate looks like any of these, depending on if we have sine or cosine. And yeah, that would be a lemniscate. First year I taught this back in, I guess that'd be like 2007, 2008. School year, they always called it Linda's cats, and so that has for some reason stuck in my head every time I've seen the word lemniscates or I've taught this lesson. I always want to call it Linda's cats, and if you want to call it Linda's cats, go for it. That's a little bit more fun than lemniscates. Right, he's got a couple more here. All right, so bear with me on this. We're still using, now we're back to R, so no funny business on this one. And we've got sine happening right there. And so everything's going to be symmetric over this vertical line of symmetry at y equals pi over 2. So if that's the case, I need to make my r theta table with that in mind. Do you guys want to work the right side this time? We definitely can. I might just start here and work my way down. And so I'll start at pi over 2 and then do pi over 3. It's not really going to go in a very good order, though. I'm going to bail on that. I'm going to bail. I'm going to chicken on it. Chickening out. I'm going this way. I want to go in order on this one, so I still like to use these values. Should get the same thing if you work it the other way, but that gap is going to worry me that I'm going to get later on. All right, so I just did the last one. I want you guys to plug in your angles on this one, and let's see what we get. Now, we're probably going to have to plug in a few more values, but go ahead and plug these in, and then and plot the points, and then we'll meet back up and see if we have the same thing, and see if we can actually draw a graph from what we have. All those zeros made my graph look a little bit skimpy. Now, I probably could go through and graph these points. I'm going to get a little bit of help, though. All right, just so you believe me as to what this is going to look like. And so I am, let's go ahead and get the, let's go ahead and plot the 7 pi over 12. Okay, and so if I plug in 7 pi over 12, that would be right here. I get 2 sine, let's see, 3 times, struggling here, 7 pi over 12. So that gives me like negative 1.4. So I've got an extra point in here, negative 1.4. This was my first point actually down here. So right here. So my first 3 points are going to go like that, okay, from what I got. Well, let's go between 2 pi over 3 and 5 pi over 6. Well, we all know that's 3 pi over 4. All right, so if I multiply that by 3, that's going to be 9 pi over 4. That's going to help me. 2 sine, if I can just type in 9 pi over 4, it's positive 1.4. So I'm wondering that I get a bunch of 1.4s in between. So 3 pi over 4, 1.4. So it comes up, and it's going to tag the 5 pi over 6 right there that we got. Let's just do this one. What would that be? Let's see, 12. So 11 pi over 12. that would be in between right here. If I do 11 pi over 12, let's see, if I multiply that by 3, that's going to be 33 pi over 12. That's going to help me. So 2 sine of 33 pi over 12, positive 1.4 again. That's good. That makes sense. I'm going to come down and get 1.4. And then this pattern is just going to continue. I'm just going to keep getting 1.4 each time I go out. I get 1.4. If I was to plug in this value right here, 4 pi, halfway between 4 pi over 3 and 3 pi over 2. Let's see, I have 11, 12, 12, 13, 14, 15, 17 pi. Okay, let's just plug that in. So 3 times 17, that's like 51. So 2 sine of 51 pi over 12. Yeah, 1.4. Okay, so 1.4 would be where I'm at right here. So yeah, this just comes down. Forms this nice little symbol curve right here. Kind of looks like a flower, which is good because it's called a rose curve. Okay, a rose curve. A couple things I want to point out to you though before we get off of this. Let me erase that out of the way. See this number 3? Look how many petals I have on my flower. I have 3. It's not a coincidence right there. That's going to happen every time that this, we call it n right here, every time that the number in front of my theta is going to be an odd number. And this has happened throughout this video so far, where this 2 is simply going to be the length of each petal. As you can see, each one is 2 units long. And so that's where the 2 comes into play. It did the same thing on the circle, and it did, which a circle would just be like 2 sine theta, right? 2 sine theta. Well, that's the same as 2 sine 1 theta. It's a flower with only 1 petal. We just called it a circle. Now, there's a couple of different ways that this could look, and it's going to be a little bit weirder whenever n turns out to be an even number. So it works for both cosine and sine. And if, like I said, we worked one, looked very similar to that. If n turns out to be an odd number, then that's how many petals you're going to have. Okay? If n, whether it's sine or cosine, if n turns out to be an even number, then you're going to have twice as many petals. Okay? You'll have 2n petals. Now, I'm not going to go crazy with this and give you something like that's going to have 16 petals or 20 petals or anything like that. It's really fun to graph in a graphing calculator if you've never done it before. You have to change a couple of your settings around, and you can get your graphing calculator to go nuts on this. But nothing I'm going to be looking at in this class. Okay? So I'm going to pause the video, and I'm just going to work this one from start to finish. I encourage you to do the same thing. Let's change one thing, though. Like I said, I'm probably not going to give you anything that big. Let's just make it so it's 2 theta and work it out with that. Okay, so hit pause. I'll work it from start to finish, and we'll see if our end product looks the same. It's going to be a rose curve again, since it's in this form. Haven't connected my dots yet because I'm afraid that maybe you guys got off a little bit. It's very important to connect these dots in the order in which you made them on the table, especially the rose curve. I mean, you can kind of see what the rose curve would look like, but if I connect them in the order I made them, it made this much. Okay, but that's enough to get a start because I know that I'm gonna round about this curve here and come down, and I still am connecting them in the order from 0 to 2 pi, but this would be my final answer. It's going to bother me. So that would be my answer on that. A good rose curve. Again, it's got a petal length of 2. Notice how many petals it has this time. Since 2 is even, it has 4 petals, petals. I think it's a T, petals. Practice that, start to finish on your own. We have one more that I'm going to talk about. I don't plan on putting this on any assessment, so this will just kind of be extra, but it's kind of fun to do. And so there's no sine, there's no cosine, but it tells me it wants me to go from 0 to 2 pi on it. Okay, I'm gonna jump around a little bit. You'll kind of see why. I'm gonna make it so I can get around this circle a little bit sooner. Let's see, 5 pi over 4, 3 pi over 2, I think 7 pi over 4, getting close into that screen. And so it says whatever r is, theta has to be also. And whatever theta is, r has to be. So if r is 0, theta is 0. If theta is, oh my word, see, I told you I was going to do that. I told you I was going to get them on the wrong side. And luckily for us, this time it doesn't matter. All my thetas are supposed to be over here on the right side under theta. But it doesn't matter this time because whatever r is, theta is going to be. All right? And so, let's see, pi over 4, that's like 0.8. And then pi over 2, well, I know that's like 1.57. 3 pi over 4, I don't know what that is. 3 pi over 4, 2.4. Pi, 3.14. I don't know what 5 pi over 4 is. Sorry. 5 pi over 4, might as well be 3, that's 3.9. 3 pi over 2, that gave me 4.7. And 7 pi over 4 gave me 5.5. Even if I was to do 2 pi, if I was to plug in 2 pi, I would expect to get 6.28. So whatever theta is, r is, whatever r is, theta is. I even got my table backwards on this one. It doesn't matter because everything comes out the same. So I get 0, 0. And then I did pi over 4.8. So I just came out to right there. Pi over 2, 1, about 1.5, 1.6. 3 pi over 4, 2.4. Let's see, 1, 2, wrong line. 1, 2.4. Pi, 1, 2, 3.14. 3.9, 1, 2, 3, almost out to 4. Kind of see what this is doing. What am I at? Oh, 4.7. How'd I go 3 point? It should be 3.9. I did 3.9? 1, 2, 3. Yeah. And then 4.7. 1, 2, 3, 4. 0.7. 5.5. And then like 2 pi, I'm like 6 point something. I don't know why I switched colors halfway. Get this fun shape. Okay. And yeah, this one actually is a spiral. That's the whole thing. There's no reflections on this one because it didn't have sine or cosine. And it's known as the spiral of Archimedes, or Archimedes spiral. And so I've got a couple different ones here. One looks like the one that we did. The other one, it goes from 0 to 4 pi. You can just see it's just forming that nice little cinnamon roll figure. Okay. Long video today. I hope you took a couple days to get through this. If not, I would definitely take a break and let all this soak in. These are the practice problems that I would like to see you work. I'm going to try to model the test after problems that look like this. So we'll have a Q&A over this. If you have a question on one of these, have it ready, and then we will talk it out together.